what do you think, like, how do you think I should phrase the fact that I want to be the best engineer? Should I say, like, I want to be the best electrical engineer in modern history, or just in all of history?
Modern history is a nice touch, but
Like, what
no,
would
I
that?
want to. I like a different, not a want. It's a aim. It's a goal. So like I aim to be the best.
Okay,
Something like that.
strive.
I strive.
Okay, okay, yes. Maintain the modern history. I strive to be the best electrical engineer in modern history. Yeah.
I kind of
Okay.
like that.
Okay.
Modern.
And I'm gonna write it on my paper. Let's make it real. Let's manifest it.
Whisper it to Mina's ears, and the manifestation will start.
I strive to be the best electrical engineer in modern history. Meow. Yes, sir, Mina. In modern history. Because what would that really entail? Like, how far back is modern history?
I don't think it has to entail anything, but I think it's just to make it clear that like there already has been very best, and you are the next best. So as in modern.
Right, okay. Fair. Fair. Okay. Alright, so I'm going to jump into the Colpitt's oscillator. Right, they have very different, very distinct topologies, but we're going to look at this particular one where we tap the feedback in between the series inductor and capacitor. And then we have our second capacitor in parallel with those two. So I'm going to draw it out. First, we're going to start with a bias point operation of our 2N3904 NPN BJT bipolar junction transistor. We're going to begin with this, and we have to set the operation point. So we're probably going to run an approximately 2 milliamps current through our collector, and therefore if we assume a gain of 100, we're going to have a base current of 2 milliamps, 0.002 milliamps, or what is that, 2 microamps? Let's see, let's write it down. I'm not sure. I can't think of the conversion right off the bat. I think that's correct, but let's see. And I am recording perfect. Okay, everything's good. Excellent. All right, fantastic. All right, and I already have my supply configured. We're going to have this transformer. It's a step-down transformer from 120 volts AC to 20 volts AC through a full wave bridge rectifier. This is going to convert the 20 volts AC into 18 volts AC or 18 volts DC with and then obviously an approximate voltage drop of 2 volts, right, to get us to that 18 volts DC. Then I run this through this voltage regulator right here, the L7809, where the last digit indicates the output voltage, L7809 being 9 volts. And so that means that's going to be our supply voltage, or our VCC, into our oscillator. Nine volts. So we're going to want to label everything. Okay, these two are grounded here. This is going to be our emitter resistor, RE. We'll consider this R2, R1. and RC, right? This is the collector. This is the configuration of the NPN BJT, where we're going to have an output here. Our arrow is facing this way. We're going to have a decoupling capacitor here so that none of our DC transfers through to our LC tank. We only want our AC getting through, and so this DC coupling or this decoupling capacitor opposes our, or attenuates our DC, I suppose we could say, and passes the higher frequencies, right? DC essentially would be a frequency of 0. It's a direct current. And now this is our topology for our specific Colpitts oscillator. We're going to tap here in between the capacitor and inductor, and then we have the second capacitor in parallel. Grounded here, and this is our feedback network right here. Again, another decoupling capacitor here. And another another aspect or another purpose of the decoupling capacitor is so that we don't alter with the other elements which are used in the LC tank circuit. None of these elements are going to affect our DC bias point, right? Because we don't want any of these parameters to change. That would affect our DC current gain, which is denoted as beta or HFE. This would also, and therefore that would impact things like voltage gain, etc. So we want to maintain that DC bias point at all times. That's why we add these decoupling capacitors. Okay, let's label this L. We'll consider him C2, C1. And then we're not going to label our decoupling capacitors. Those are fine. They're not much to consider. We just want them to be a high capacitance, right? Because the formula for impedance of a capacitor is 1 over omega C, where omega equals 2 pi f, 2 pi times the frequency. Therefore, the lower the frequency, the higher the impedance. The higher the frequency, the lower the impedance. So with a low frequency, such as DC, we're going to have a high impedance, and this will not pass through. It's attenuated. So that relationship defines exactly why we add those capacitors there. I need to zoom in just a little bit. Yeah, that's good. Like that. Okay, very well. Check. Okay, good. And my mic's on. Yeah, okay, cool. Yikes. Better make sure. Okay. Okay, so first thing we need to do before we do a small signal analysis is that we need to set the DC bias point, the operating point for our transistor. And again, we're using the 2N3904. This is an NPN BJT. Okay, so first thing we're going to do is we're going to assume some values. So let's first set the desired collector current. So we're going to say IC equals, let's go for 2 milliamps. This is what we desire. Okay, IC equals 2 milliamps. We're going to assume a value of 100 for our DC current gain, right? We're going to denote this with beta. So our beta equals 100. Therefore, the way that the NPN transistor operates is that it operates on current, right? So if we have a gain of 100 and we have approximately 2 milliamps flowing at the collector, then our input into the base of the NPN transistor is going to be IB equals 2 milliamps divided by 100. Okay, and this is going to equal 0.002 milliamps, 0.02 milliamps. Therefore, this equals 20 microamps. 20 microamps. Okay, these are just other ways we can denote it. It's a conversion of units, and so these are important to consider. Okay, so after we have that, now let's consider that it's just an inherent property into the inherent property of the NPN BJT is that the let's denote these. This is the base, this is the emitter, this is the collector, right? Okay, so the voltage across the base to emitter is going to assume a value of 0.6 to 0.7 volts, right? So let's just find that sweet spot in between and assume that this is going to be 0.65 volts. Now, with that considered, the other property that we want to maintain is we want to have about like 1 volt across the emitter resistor. Now, this reason I haven't fully come to a conclusion on. I don't know exactly why we want 1 volt here, but as we do our calculation, perhaps it might come to we might come to an understanding. So that's another assumption we want to make, is that we have 1 volt across the emitter resistor, right? So positive, negative here. We're having current flow in this direction, right? So we're having current flow in this direction. This is our emitter resistor, and our voltage across the base to emitter across our transistor is going to assume a value of 0.65 volts as long as we're operating in the active region or in saturation. Okay, and therefore we are, right? We want to set it up for saturation. Okay, so with this being said, right, we can already assume that the voltage across R2 is going to be 1.65 volts, according to Kirchhoff's voltage law, KVL. Okay, so 1.65 volts. Okay. Oops. R2. Now, another practical application or something that you could perhaps derive from the physics of everything, but we're not going to take such a deep dive. We're looking at the practicality of it, and this is an assumption that's common throughout designing Colpitts oscillators. Maybe oscillators, well, just this topology, considering that we're using a common emitter amplifier, that's this stage of the circuit, and this stage is what defines it as a Colpitts oscillator, how we're tapping in between the inductor and the capacitor, right? So considering that we have a common emitter amplifier, we're going to want approximately 10 times our base current to flow through R2, or rather we want to establish a current of 10 times the base current so that we can guarantee that our base current is somewhat around this value of 20 microamps. So that's going to look like this. We're going to set, let's consider it I2, right? That's the current flowing through our R2, I2. Now if we have this is going to equal 10 times IB, right? And so this is going to equal 200 microamps. And that's good. We'll maintain that unit of microamps. Okay, so that's good. So now considering that we have I2 and we have our voltage across R2, we can go ahead and derive the value for R2, right, through Ohm's law. And that's going to look like this. R2 equals 1.65 volts divided by 200 microamps. Okay, and 0.65 divided by 200 e to the negative 6, right? If we're going to use engineering units, right? Otherwise it'd be times 10 to the negative 6. Same thing though, it's equivalent. That gives us a value of 8,250. Okay. All right. 8,250 ohms. Okay, so that's fine and dandy. But the thing is that what do I actually have available for resistor values, right? Because we want to build the circuit. We want to take theory and realize it in physical form. So let's see what values I have available. Well, I'm not really liking the values that I have available. It's not good. Not good at all.
Resistor.
Yeah, resistor values. I guess I've 2.2k. I have a 5.6k. 7.8k. I have 7.8. Wait, what if I had? That's gonna be too much. Wait, 2.2.
You need a lower value.
4.4. No, that's even more. Yeah, I mean, I could put two resistors in series and they would add. I don't really have anything close to 8,250, I think it was. So, I have a 2K. Wait, a 2K. Okay, 2K. I can get to 8.7. And what was our value? 250. That's not very good. Otherwise that would be 7.6. All right, let's do that. Let's do 7.6 and we'll move from there and calculate everything. That's good. Wait, I also have a 1.5. What would that put me at? 6 point, no. Wait, 1.5. Okay, that'd be 3. Oh, 8.6. No, that's good. Yo, I need to how come I don't have anybody watching right now? It's kind of bullshit. I usually get I've had 10 people join before. Why maybe just bad time of day, huh?
12 p.m. lunchtime.
Yeah, everybody's busy and shit. I need to spark up at nighttime when nobody has anything to do or something. Yeah, but also I'm kind of consider what portions of the stream or the video, whatever it is, could I take and put on TikTok? What's an interesting portion of the video that would be
You need to have something like a cat flying through your, and then that gets clipped, and then people go watch your video.
Okay, but I don't have a cat, so.
Okay, I guess we gotta solve that.
Oh no! Catch one of the strays. They go crazy.
Have they been eating the food?
I mean, I haven't given them anymore.
Oh.
What'd you do with it? Where is it? Oh, it's in the cat. Yeah, I know where it's at. Ooh, I got a Zener diode in here. Okay, cool. Okay, anyways, back to what we're doing. So let's do a value of 7.6. I mean, with more resistors I can get closer, but it's a little much. 7.6. 11, 8.1. Okay. Yeah, let's do that. I can get 8.1. 8.1 ohms by using 3 resistors in series. It's more than I wanted to, but let's try to get as close to this value as possible. Okay, so R2 equals 8.1. 8.1 kilo ohms. Bang. All right. Okay. 8.1 kilo ohms. Okay, so with that value, we want, okay, with that value of 8.1 kilo ohms, we're gonna have, let's maintain that voltage. So 8.1, so okay. So I2 now, let's recalculate I2. 1.65 volts divided by 8.1 kilo ohms. That's going to give us a current of I can't believe my calculator's almost dead. E to the 3. Okay, so it's going to give us 203.7 microamps. Okay, so it's a little more. That's nothing bad. So 203.7 microamps. That's going to be I2, so let's divide that by 10. Then we can assume our base current now is IB equals 20.37 microamps, 20.37 microamps. And we can assume our collector current is now 20.37 microamps times 100, right? Because we have this DC current gain of 100, our beta, is going to be 2.037 milliamps. 2.037 milliamps. Okay, so we can assume that. So it's a little bit larger. That's fine. That's good. Okay. So now with this current, we're going to have that. Another assumption, and we want to have our current across our collector resistor. We want half. No, let me rephrase that. We want half of our supply voltage across the collector resistor for the fact that we want to allow maximum swing, right? We don't want any distortion of the output signal. And if we have anything less than, well, that depends on our output voltage, right? I guess if we have a supply of 9 volts, then we're going to have half of that be 4.5 volts. That means we can have a maximum swing of, what, would we have that again? 2.25 volts. That maybe could be our maximum swing, maximum output before we perceive any distortion. That might be true, but anyways, that's pretty much what we're shooting for, is that we want to allow maximum swing so that we don't clip any of our sine wave, because our sine wave is going to be the output for this oscillator. And then in the future, I want to run this oscillator through we have to run it through a buffer and then to a Schmidt's trigger in order to convert it into a square wave. And a square wave can be used for like clock signals, used in memory elements such as flip-flops, which flip-flops make up registers and components of computers and stuff like this. We can also use square waves for pulse width modulation, used in boost converter, used in what else is pulse width modulation? Used for like the control, very high precision control of motors, like servo motors and stuff like this. So it's real nice and dandy.
Super nice.
Yeah, come on, cool. Yeah, come on. Blame me, dog. Hey, yo, look, I also found this too. It's called alum, right? And it's just potassium aluminum sulfate.
Whoa.
Yeah.
It's like a kitchen salt?
Alum. Yeah, pretty much. I don't know what people would actually use it for in the kitchen, but yeah, that's what it is. But
I know it's like MSG, or is it very powder like?
It's granular. Like, it's not powder, but it's like sugar.
What would you use it for?
What, to make like an electrolytic solution? You could convert this into aluminum metal.
What?
Yeah, I think that's what I was going to do. I wanted to convert it into aluminum, or I want to convert it into sulfur, right? Because it consists of potassium aluminum sulfate. Although to extract the aluminum, I think would be easier because potassium sulfate is that like positive negative ion. You know what I mean? But also so is, wait, no. Aluminum's not an ion. What is the, or it is, isn't it like +3? Something like that.
Aluminum? Let me see. I know my professor last class just said to never heat up aluminum because it's very dangerous fumes.
Oh. Yeah. I've done,
It is?
Huh? Oh, well, I just, yeah, I'm sure any metal, yeah, any hot metal, I guess maybe not so much. I guess, welding is an entirely different thing because it's completely, vaporized. So, I've been around a lot of welding. A little aluminum welding, not much, though.
Mm.
Okay, so we've defined our collector current. Okay, and now, oh yeah, okay, so now we're gonna assume half of the supply voltage is across our collector resistor. We know our collector current. I'm going to get rid of this value here. I'm only going to specify or like label things here, and then I'll write the values down here. We know our collector resistor current. We know the voltage across it, which will be half of 9 volts, 4.5. Therefore, we can find the value of RC, and that's going to be 4.5 volts divided by 2.037 milliamps. Okay, and this provides us with a resistance value of, let's see, 4.5 divided by 2.037 times e to the negative 3. Yes. 4.5. That's going to give us a value of 2,209. Okay. 2,209 ohms. Now 2,2.2. Okay, I literally do have a 2.2 kilo ohm resistor, so that's gonna be perfect. That's what we want. Okay, so I'm just gonna get rid of that 9, and we got 2,200 ohms. That's perfect. I couldn't be more satisfied with what I just calculated right there, because that is perfect.
Oh yeah.
I don't know what I did with my resistors though now. Oh, okay, I found them. .2 kilo ohms. Fantastic. Okay, so now with that value, we can go ahead and find R1, which I guess we could kind of do, wait, 2 of ways. No. So, okay, so we can go ahead and figure out the voltage across R1 by subtracting 1.65 volts, our voltage across R2, from 9 volts, our supply, right? Because these are just 2 series resistors that drop into the ground. So 9 minus 1.65 is going to give us 7.35 volts. So V2 is what we'll call it. That's the voltage across R2. That's going to be 7.35 volts. And now if that's the case, let's see. We can go, so now that we have a value of R2, we can go ahead and find the best value for R1 using the voltage divider relationship. So the way that we would write this is we're going to solve for R2, so we can say, what would be the best way to do it? It doesn't really matter. Let's just go ahead and write it out. So 7.35 volts, our voltage across R1, equals 9 volts, our supply voltage, multiplied by R1 divided by R1 plus our value of R2, which is 8.1 kilo ohms. 8.1 kilo ohms. Okay, so we go ahead and solve for this. 7.35 divided by 9 gives us, wait, what did I do? I wrote it wrong. 7.35 divided by 9. Okay, 0.81666667776767. Oh, brother. Okay, so 0.8167 equals R1 divided by R1 plus 8.1 kilo ohms, right? We're going to multiply that by that side, and then we're going to say, and then we're going to subtract it from the other side. So I'm just going to go ahead and jump ahead. You can figure out the math yourself if you're not a complete R word. I'm on YouTube. They'll get me for it. I'm on YouTube. They'll get me for saying things.
Look at you for saying that.
Huh?
Just saying that, look at you.
Nah, no they won't. No they won't, because the AI won't be able, it doesn't know what I'm talking about. All right. The AI surveillance state doesn't know what I'm talking about, okay? There's many words that begin with R, so.
Okay.
It's a word very similar to that word which describes fire resistant clothing. You know, it's another word for fire resistant without the "ant" at the end. Yeah, only high IQ people will understand, right? Look it up. Another word for fire resistant. Look it up. Okay, so 1 minus 0.816667. Let's do that. And then we also have 8.1 E3 times 0.816667. Okay, and that's... You found it?
I did.
Cool. Equals 0.18333 R1. Now 6615 divided by 0.1. Let me just use these whole values. That's better. Oh man, you can't see the calculator there. Bang. Okay, so our collector resistor... Oh no, I was solving for R1. Wait, okay, let's ensure that makes sense. So, because that's a pretty high value. So R1 equals 36,081. 36,081 ohms. Okay, so if that's the case, let's ensure that makes sense. So 35 volts divided by this is around... 6 is around 203. Wait, and that's exactly our I2, 203.7. Okay, yeah. So that everything adds up. Everything adds up. We have the same current as we have, approximately the same current as we have running through R2, and therefore that would make sense. Okay, so approximately this value. Now let's see how we can actually make that happen with the values that I have here. That's pretty high. Let's see. Let's see. I have 22K. Oh, I have 15K. And we want 36. So I could do two 15Ks and a 5.6K. So 15K, 5.6K. That's going to give me 35.6. And we want to get to, let's just get to 36. So like a 400, 470? I have a 470. Ooh, the other thing we could, no. Or yeah. Wait, let's see what a 47 kilo ohm in parallel with a, 47 kilo ohm in parallel with a, 22. Let's do that. Let's see what 47 in parallel with 22 would do. So that's going to look like this. So 47, yeah, we can just use the value of 47. That's fine. So plus 22, power, or 1 over that, and then now invert that. Oh, that's way smaller. What the hell? Okay. That's way smaller. Alright, fine. We'll just maintain the track I was on. So 15K, 5.6K, and like a 470 will get us there. Which I'm pretty sure I have. Oh, here it is. Bang. Okay. I need the 2K, 22. I don't need that. I need 2.2. I will need that, and that's it. Okay. Okay, and our actual value will be, so what? We have 35.6, we have 35.6. We have 3670. So 3670. Wait. Oh shit! Did I not do that right? No, it would need to be wait. Yeah, 4606070. Oh shit, that's super close. Okay, that's perfect. Okay. Damn. Okay. R1. Did that. Did we calculate our value for RC? We did, and I have that value. What are you watching me? Oh, yeah. Okay. Okay. All right. Okay, our emitter resistor now. Let's see what our value for the emitter resistor will be. So our emitter current would be the addition of our collector current plus our base current, right? But our base current is 100 times less than our collector current, so perhaps we can just assume that our emitter current would be the same as our collector current. So if that's the case, we have 1 volt across our emitter resistor. Therefore, 1 volt divided by our collector current, which is 2.037 e to the negative 3, is going to give us a value of 490, which I have 470. I have 470. Should we? I think. Do I have 20 ohm? 20 ohm. I had a 22. Perhaps let's do it. Let's get as close as possible, so that we can maintain these values. And you know, we can take the multimeter and we can measure the current, we can measure the voltage, and we can see how these our, you know, what do you call it? How our measured values compare to our theoretical values, right? That's going to be interesting. So yeah, so I only have 22. That's fine. That's what we use. So therefore, if I have 470, so I'm going to have 492 for our value, of RE. So RE equals 492 ohms. Okay. And now another thing is RE is going to, the emitter resistor is going to affect our current gain, or no, our voltage gain. You know, so when we do the small signal analysis, we're going to have to consider the value of our emitter resistor. A way around it is that we could add another, so in parallel to the emitter resistor, we can add another resistor and a capacitor, right? And so at low frequencies, the capacitor will attenuate, or rather, act as an open circuit to low frequencies. But at high frequencies, at our operating frequency, the capacitor will act as a short, right? It'll have a low impedance. Therefore, the high frequency signal will run across the resistor that is in series with the capacitor. And if that resistor is a far lower value than our emitter resistance, then we've increased our voltage gain. But there are, limitations to this. So we'll go ahead and continue with this analysis and see how much the emitter resistance affects our voltage gain. Because that's kind of like, I've already achieved a value of 700 millivolts with a previous design of the oscillator, but it's just not enough. I need around 1.2 volts, and that's kind of like the minimum value that I need. So okay, now with these two, we're capable of doing that. Okay, so now we've fully biased our transistor to operate in saturation, or the active region, whatever you want to consider it. So now we should operate on amplifying properties. One thing that we can do is we could go ahead and get out the multimeter and go ahead and measure our values that we have and compare them to our theoretical values. We can also input a signal to the amplifier, and we can measure the output of the amplifier, and we can, we can measure our gain, right? We can compare the output voltage to the input voltage and measure our gain, right? Because I have an auxiliary cable here with an aux port that I can plug into my phone. My phone has a signal generator on it, and we can have 2 channels recording on the oscilloscope. We can have one channel recording the in, which would give me my voltage value, and then our out, which would also give me my other voltage value, right? And then we can compare the 2 values to calculate our voltage gain. That's probably going to be much easier than trying to theoretically calculate voltage gain, because that's actually quite a lengthy process. That's actually the first time I've had that idea, and I think that's the best idea. So let's go ahead and make this common emitter amplifier, and let's measure some values. So I'm going to pull everything apart now. And we're probably going to have to, honestly, I should just pull everything out of here. And short circuit your capacitors, right? We don't want them to hold any charge. I would hope that everything was already short circuited through the resistance values, but, or rather, the energy was dissipated through the resistors that were connected in the network, but you can never be sure, so rather safe than sorry. So we're just going to go ahead and short circuit all of these and ensure. Okay, we'll leave the resistor there, and make sure that's short-circuited. Oh shit, no, that's fine. And those will stay. That's all part of the power supply. Okay, so we just have our transistor here. Excuse me. Okay. Alright, so let's start with R1, 3670. And the way we're going to do that, 215K. It's going to be a lot of resistors, but I want to maintain these values.
Can I see the board when you're done?
Yeah. Yeah, I'm just gonna. You want to pull up my stream and see how it looks?
I can do that.
Okay. Okay, so the way that the transistor is oriented, right? It's emitter, base, collector. So this is connected to the emitter from the supply. Okay, so it's gonna look like. How's it look?
It looks nice.
Does it? Is it like? Is it pretty easy to see? Make sure that you're in 1080p.
Maybe I'm gonna pull up my phone because I can't hear the audio.
Oh. It is rolling, yeah. I do got the audio going, so it should be good. Yeah.
I hear it.
Okay.
Maybe I'm gonna pull up.
What?
No, it's just my voice.
Oh, yeah.
No, it looks super good.
Does it? Okay. What would it... no, it's good, right? It looks nice.
You didn't put the new camera to use yet, though, right?
No, not yet. I don't even know if I have another USB port on my computer, actually, so we'll have to figure that one out. But yeah, I'd probably do that one on the soldering station. Yeah, because I think that would be the best use for it. Yeah.
I think so.
Right? Because, I mean, this is good enough for the theory and the circuit, right? I mean, is this like, or should I have a separate one for the circuit? Like, it could come from, I don't know, like, I'd rather use it for the soldering station. Okay. All right, so we have our 215K. What else now? Now we're going to use so that gives us 30. We wanted a 5.6 and a 470, right? Okay. Okay, so 5.6. Oh my gosh, this is too many resistors already. I don't like it. Let's get these real close together, like this. You gotta go here, like this. Okay, and then we got him here. Oh, you don't want to go on. I'll put him here, actually. Okay, that was our 5.6. Now our 470 can go straight to the emitter. Wait, straight to the emitter? No, straight to the base, I mean. Straight to the base. Right, just like that. Okay, that's our 470. So now we have, right, there's some tolerances on the actual value of the resistance itself. So we have approximately 36,070 ohms right here. Okay, with all of these series resistors. So now we have this connected to our base. Now we need to go from the base to ground with our value of R2, which is 8.1K. And the way that we're going to do that was with a 5.6 and what? Oh shit, I should have wrote that out. 5.6, what? 7.8. Wait, 5.6. Wait, 492. 5.6 plus 3, 8.6? No. 7.8. R2. What else did I have? 4? No. 7.6. What the heck? How did I get the value of 8.1? So definitely a 5.6. Okay, so he's going to connect to ground. Not directly, but we have to have the other resistors in series. But from the base, right, to the other series resistors to ground. So I have 5.6. What? If we did 2, that'd be 7.6. And then a 470, 7.6, 8070. That's really close, but how did I get that before? What, 5.6, 7.8? And then I could have got closer to my other value with the. No, that would still be 7.8. It'd still be something similar. Okay, that's fine. Okay, so 5.6, let's go 2K. Wait, no, that would give us, yeah, because that'd be 7.8, and then we could add that. So if we go 5.6, 2K, 7.6, 470, that's going to get us right there at 8,000. I have no idea how I got 8.1K. What the hell? 3. No, that would have been 8.6. Weird. Super weird. Okay, that's fine. Let's do this. Bang! Let's go. Fuck yeah. Oh, shouldn't curse though, right? Maybe kid friendly or fuck that, right? Who's this for? All right, who's the what do you call it?
Target audience.
Yeah, the target audience. That's it. Who is the target audience?
Me.
Oh yeah, that's okay. That's very good. Okay. So what? This is gonna put us at so 5.6 with a 2K, 5.6, 7.6. Then we do the 470. That's gonna be 8,070. I guess I don't know how the heck I got 8.1K earlier. That's crazy, but this should be good enough. Makes me want to recalculate all of my values, but whatever. Okay, we cannot have those two touching. Hell no. Bang. Okay, got that. Okay. Let's look at our emitter resistance. So we have 492 ohms, 492. How did I get that? I used a 470 and a 22. Yes. Okay, so that's easy. Okay, so we're going to have the 470 first going from the emitter. And we can't have him connected there. That has to go there. Oh, this is such a mess. It's going to look like shit. It'd be like, look at how confusing this is. Like, this is something that, like, can you even tell what's going on here? Do you even know where the lines trace?
Your circuit?
Yeah. No.
I just see a lot of resistors.
That's not fun, but I guess it is what it is. Like, I have to get to these values as close as possible to our theoretical values so that we can make a comparison. Now, considering that I don't actually have 8.1K and I have 8.07K, now I want to recalculate everything, which is kind of some bull. But let's just see what our measured values are. Let's see if we even have amplification, okay? All right, and this was our 22. So this 22 is going to connect from our 470 in series with our 470 directly to ground. Yikes. This is quite the mess. Yikes. All right, that will do it though. That will do it. And then I have to get a connection between this ground and this line here. Now we've made a new ground. That's good. Got some more room. Oh, it's right there, those two. Man, I could really use a Celsius right now.
Okay. I'll keep that in mind.
Oh, will you give me one today?
Yeah.
Okay, I might have to go before you get me one though, because I do want to go to the gym, and maybe I'll grab one before the gym.
Okay. And then the one I get you will be extra.
Yes, extra. You guys, I'm so in love. You guys, chat. So in love, chat. Okay. All right, cool. That's all looking good. Make sure that none of your other none of your leads from any of your elements are touching, right? Like this guy, he's grounded, but he's almost touching the positive terminal of this capacitor here, which is going to be all hell. All hell is going to break loose. We're going to fuck everything, okay? So don't let it fucking happen, all right? Okay. All right, and now our collector side. Our collector resistance. You good? Has a value of 2200, and we have exactly that. We have a 2.2 kilo ohm resistor, so that's perfect. Just one resistor. Ha! That's beautiful. This is what we desire. Indubitably. Do I have one out here? I don't. Okay. All right, and he's gonna connect directly to our supply, so we'll figure that out in a moment. Okay, all right, now let me find my aux cord that I can connect my phone into and provide some signals so that we can measure with our oscilloscope the input and output voltages. Oh, here it is. Bang. If you can see, it's real thin wires, and I soldered. Oh man, for a moment it focused. For 1 second it focused, and it was sick.
Go really low. Up. No.
Are you kidding me? It's not gonna happen? Anyways,
Do it with
okay.
your full palm.
Huh?
No?
Oh. It did again for a second. Whatever. Okay. Anyways, yep, we got this. So we have a. Oh. Man. Now I gotta look up the pin out for the aux. I don't know why I cannot ever fucking remember. I've looked this up so many times. I can't ever. Just the pin out for the aux. Like, because I got 3 wires here. One's a supply, one's the ground, and one's the signal, right? I assume, but it's like I always forget. I have to look this up every time. So let's do that. Watch this. Are you watching the stream right now? Oh, but I don't have my... I don't have the new camera set up for it. Oh, no. That's fine. I guess I'll just get rid of my camera for now. Oh, no. I should be able to copy it. Wait, I should be able to copy it. So, wait. Hold on. Watch, I want to show you something cool. Paste. Okay. Wait, delete. Just one moment, ladies and gentlemen.
Yes, sir.
Okay, perfect. Get rid of this. Remove. Yes. Get rid of. Nope, not that. Wait. Actually, yeah, get rid of that. Remove. Video capture. Is that one? Yeah, that's the one. Remove. Almost there. And I just want this. Copy. Paste. Okay, now I got it. Cool. That was pretty quick. Okay, so, bang. Okay, oh yeah. Did you see it?
No, it's it's a little bit behind, so I'm waiting.
You're on YouTube? Yeah, I think that's much more behind than Kick is. You know, the streaming platform Kick? Ice cream truck is here. Okay, I don't have a mic on this, so ground, left, right. Oh, it's a left, right distinction. Okay, so it's not like signal, but it's left, right. So, wait, left, right. So I just want to put them both into the same, I'd want to put them both as input then, if that's the case, left, right. I want to like superimpose them and have the highest signal. Or maybe we should just do one for a lower signal. Or perhaps it doesn't really matter. So let's see though, because I have, what colors do I have? I have green, red, and like yellow. So let's try to find a comparison. Nothing yet? Oh yeah, you got it. So you see how I switch between?
I like that.
Cool. None of these are really showing me the colors that I want. Green, red, and yellow. Obviously, green is probably ground. Red is, you know what, fuck it. Let's just hook it up. See what happens. Oh yeah, so let me transition back now. Yeah, let's just hook up and see what happens. I'll move that resistor back a little bit, and then we're gonna connect right there. So we're gonna put, oh, it's blue. It's not even green. Oh man. Oh well, let's still see how that goes. I don't think it's gonna really hurt anything if we get it wrong. But I definitely don't want any short circuits, that's for sure. Yeah, right, and then he's gonna go into our base. That's the signal that we desire, into the base. And this guy here is, you know, what we could do first though, yeah, but does that, no, that shouldn't matter. That shouldn't matter. Okay, so, and then he can go like right here. It's getting real messy. Holy smokes, getting real messy. Okay, I want to make sure that they're not touching. Good. Okay. I think that, are these wires insulated? Shit, I don't know if they're insulated. I think it's insulated, but like I'm not positive. So I don't really like it. It's gonna kind of worry me. So yeah, let's put it there. That's better. Put him in the back. Get him out of there. And then we can jump around with him like that. Oh shit, one of them broke. Fuck. I have to solder that again. Alright, get him out of there. Okay. Get him out of there too. Okay, that should be good enough. That should be good enough for what we're trying to do. Okay, make sure, no, that's touching. Can't have that touching. Okay, looks good. Looks good. And that's grounded anyways. Okay, our input is going to be, jump him from there to there. Yeah, because that's much shorter. So, jump him from here to here. That's our supply, and then we got to jump from, that's where our supply voltage will go. We want it to connect to this collector resistor, and our this is a part of our voltage divider for the base, and then we have to jump that to the voltage regulator. Okay, regulated. Regulated? What do you mean regulated?
What do you?
It's another thing, inside joke. Kind of an inside joke, like, okay, numbers guy.
Okay.
Yeah, but this is, something else. I'll tell you later. Okay, so that's the output, and then this is the input where our transformer will connect, or well, actually our full wave bridge rectifier. And then this is a port where my phone will connect and provide a signal that, I have a signal generator downloaded on my phone, so I can output a signal between I think it's 0 to 20 kilohertz, right? It's within the range that humans can hear. So up to 20 kilohertz and as low as 200 hertz. So maybe that is the lower end of it, but that's within our hearing range, and that's what the signal generator operates at. So we can go ahead and before I hook up my phone and then hook up my oscilloscope to record the signal, let's check our bias points. And so let's do some measurements for voltage and perhaps current too, although I have too many resistors here that to measure the current I'm going to have to make a disconnect, and I don't really want to do that. So maybe we'll just do some voltages. Okay. Let me make sure everything is connected properly. Double check connections. Measure twice, cut once type shit. Type shit. That's all connected. That's grounded. Make sure everything's grounded. Otherwise, you might fuck your shit. Too much?
Too much.
Okay. Alright, my bad. Hey! Yo, get that guy a job. Get that guy to work or something. Come on, all he does is lay around all day and, eats and poops. That's it.
The life.
Get that guy a job. Somebody get that guy a job. Alright, everything looks good. The only thing about my transformer leads is that they're incredibly short. So, that's not fun. So, let's see if I can get him over here. Without messing everything up right now. Okay. Rather, do I have room to do this? No, this maybe is the best. Okay, so let's get him in here. This is my power supply. Okay. Well, if anything, if it explodes, we got a clip. Yay. Okay, and I also always forget this, too. Holy smokes. About which is the positive and negative lead. Okay, down here is positive. Cool. This is positive. So he's going to connect to our voltage regulator right here. Regulated?
What do you mean regulated?
What do you mean regulated?
See, now I'm in the inside joke.
Yeah, but you don't know where it comes from or what it's talking about.
I don't.
Okay, so we got him connected. That's our supply. And now we got to ground it. Which this isn't working too well. Ah, shit. It's like, oh, okay. It's being a real pain in the fucking ass. That's pretty good. And I just need to get this grounded. Yeah, okay. Alright, that should be good enough. Looks like dog doo-doo. But alright, I'm gonna turn it on and close my eyes. Make make sure that it's off. Yeah, it's off. Okay, can you still, everybody can see that? Cool. Okay, it's plugged in. Believe everything's connected. Okay, I'm gonna shield my eyes. Turn it on. Alright, nothing blue. Alright, now let's do some measurements. Okay, cool. Okay, so we're gonna pull out the multimeter here. And now, you know, referring back to our theorized values, let's go ahead and measure around the circuit. So I'm gonna set to 20 volts on DC. Oh my gosh, that motherfucker there. Ooh, yeah, those aren't good anymore. Those have kind of broken off pretty bad. Okay, so what did we want? We wanted like 7 point something volts across our RC. So let's go ahead and measure that. Oh fuck, we have nothing. Let's see if we have 9 volts coming from here even. Nope. Okay, so something's not connected. Oh, that's not connected. I was in the wrong hole. That's what she said. Okay. Okay, let me shield my eyes again because now it's actually connected. Okay.
You need some PPE.
I have some somewhere. Okay, we have 1.8 volts. That's not good. Let's see if we have 9 volts coming from here. We do. 9 volts there. That is our collector resistor. Why don't I... Oh, yeah, wait. Collector should be 4.5 volts. My bad. It's only 1.8, though. That's not good. Across here should be the 7 all the way to the base. And what? We have 0. That's not good. Am I touching it? Oh, there. Okay, we have 8.1. Okay. That's probably acceptable. Oh, shit. Let's see what I have from here to here. What? Here to ground? That's across our emitter. Only 0.41. Yeah, I guess that makes sense, but that's not... Okay, so that's not good. That's not good. So... Shit, I gotta... oh, man. I gotta fix my setup. It's pretty bad. This is kind of hard to deal with. What the fuck? Why is it so far off? If anything, I had less of a value than my theorized value for my R1, right? I have... Wait, no. I keep mixing those two up. Okay, so... We have 35.6 and 470, right? So we have 35.6, 470. Okay, let's wait, so let's go ahead and let's measure the resistance actually. Let's just see what I have for resistance. So let's put it, yeah, to 20. No, we're gonna have to go 200 kilo ohms. Okay. So for R1, we have a resistance of okay, 11.8. Why is it so low? Yeah, so it seems because of other parallel resistances in the circuit, it's obviously pulling my resistance down a lot. Okay. Considering that we have 0.62 volts across our base to emitter junction of our transistor, we still might be in the operating or active region. So it's not very close to what I calculated. Now, why is that? I don't know, because as far as the research I've done, motherfuckers don't really take into account any other portions of the network when calculating the resistor of the voltage divider for the resistance of the voltage divider for the base. So I'm not really sure why it's being so affected. Like, right, it makes sense, if you have something in parallel, you're going to have less than whatever the value of the elements are themselves. Them in parallel will be less than whatever they are themselves. And especially it'll assume a value much closer to the lowest value if you have two resistors in parallel, one's high value, one's low value. The two resistors in parallel will assume a low value. But we might be operating in the active region, so let's go ahead and hook up a signal, and I guess let's hook up our oscilloscope. Okay. All right. Okay, this is pretty crazy, but I think it'll do. Double check everything. It all looks intact and nothing is touching where it shouldn't be, so I think it'll be okay. And I don't know what channel is which, but we'll find out. Okay, so now I need to hook up my phone. Okay. No way, did I delete it? No. Oh, there it is. Can you see that frequency generator? Shit, not completely. Over here we got more room? Yeah, right here. Okay, so as of now, nothing. I should have something though, so I got something wrong here then. I don't know. Or maybe it's my, what range am I in? What range? 200 millivolts? I think that's just noise. Okay. Oh, well, I guess that's it, because my fucking oscilloscope's dead. So, cool. That was really great. I'm glad we couldn't come to a conclusion. That's always what you want. Is to not conclude on your project. That's great. Oh, sorry. Alright, cool. Yeah, I'm just going to end it here. Because my oscilloscope's dead, so that's fucking awesome. I guess let me plug it in and charge it. Oh, I can't hear you.